Hello everyone, this is Koteswaramma, Assistant Professor of EC Department from Institute of Aeronautical Engineering, Hyderabad. Today I would like to explain about continuity equation. The basic principle behind the continuity equation is law of charge conservation. See, if you take law of charge conservation here, that explains us the charge cannot be created and it cannot be destroyed. Simply, the charge is changing its form. And for better understanding of this continuity equation, we will take a volume charged particle or a volume which is filled with a charge, and in that case, charge is represented with volume charge rho v. Rho suffix v is a representation for volume charge. And now if you take a volume and if the charged particle is moving, it looks like the charge of that particle is slowly getting reduced with respect to the time. And now here, the charge which is decreasing is changing like current. And that current is flowing out of the volume. That current we can take as current out, I out. See, what the principle of charge conservation tells us is the time rate of decrease of charge within a given volume must be equal to the net outward current flow through the surface of the volume. The same statement can be given in mathematical form as the current I out, which is coming out of the closed surface, is represented as I suffix out. That I out will be given as minus d by dt into qn. Here qn represents charge within the body. That will be equal to current or the time rate of decrement of charge, which is represented as minus d by dt into qin. That will be equal to I out, current output. Current in terms of current density. J is the representation for current density within a closed surface. Current in terms of current density, I out in terms of J will be given as, here, current density we can generally take as current per unit area. Here we are looking for current which is equal to current density into area. And now to get the current within a closed surface, we have to integrate the current density term with respect to surface, with respect to closed surface. That's why the integral here is represented as closed integral j dot ds. And now here we know qn is the total charge enclosed by the surface. J is for conduction current density. Here J is conduction current density, and if you want to simplify that equation, we have to apply divergence theorem. Here we have to apply divergence theorem to the second term, which is closed integral j dot ds. For this term, closed integral j dot ds, we have to apply divergence theorem. Closed integral j dot ds, if you apply divergence theorem to a vector, then closed integral vector term over a surface is equal to divergence of the same vector over the volume. So now here the vector is current density, which is j. Closed integral j dot ds is equal to divergence of the same vector. That means divergence del dot j over the volume. That is represented with equation 2 here. But now here if you take the other term, minus d by dt of qin, that minus d by dt, here qin belongs to a volume. Here charge within the volume generally we represent with rho v. This is a representation rho v. Then it is minus d by dt. Qn can be replaced with integral rho v dv. Now that term we can rewrite as integral dou rho v by dou t into dv. Now we are trying to substitute integral j dot ds and minus d by dt of qn in original equation. That means in the statement of continuity equation. By substituting both the integral j dot ds and minus d by dt of qn in the first equation, then we will get del dot j into dv. This equation, integral del dot j into dv equal to minus integral d rho v by dt into dv. Now both LHS and RHS integrals are with respect to volume. So we can compare their magnitude terms. Here by comparing the magnitude terms, the term obtained is del dot J equals to minus dou by dou T of rho. This equation we can take as continuity equation or continuity of current equation. And to get this equation, the basic idea is principle of charge conservation. If you want to recollect this continuity equation, for that one we have to tell the basic principle behind the continuity equation is law of charge conservation. From that law of charge conservation, what we can understand is here the charge is changing its form like current. Within the given volume, we are taking that one as a charge, and now that charge is flowing out as current. So within the volume, now its energy, its form of energy is charge, and out of the body, the energy is current. That is represented mathematically as I out, which is net outward current equal to minus d by dt of q in. And now here we are trying to take current in terms of current density. So finally, by applying divergence theorem, why we are applying divergence theorem here is we are taking charge within the volume and current we are calculating for a surface. So to get the relation between current and charge here, we have to convert surface into volume or volume into surface. So here I am trying to convert surface into volume. To convert surface integral into volume integral, we have to apply divergence theorem. So by applying divergence theorem, closed integral j dot ds, this term, this equation 2 will become integral del dot j into dv. So now by rewriting integral j dot ds as closed integral del dot j into dv, and by replacing q in with integral rho v dv, finally we can compare both current and charge terms. Finally, current is expressed in terms of current density and charge is expressed in terms of volume charge. Q is finally replaced with volume charge term rho v. So the final equation we got is del dot j. This equation del dot j equals to minus dou by dou T of rho v. This equation we are calling as continuity equation or continuity of current equation. So from this continuity equation, we can define a term which is a relaxation term. So to derive the relaxation time, here I am taking Maxwell's first equation. If we take the Maxwell's first equation, which is obtained from Gauss law, and by applying divergence theorem, then we have rho v equals to del dot d. So now from the point form of Ohm's law, we can take j as sigma into E. Okay, now by taking that j and by keeping that one in mind, we can rewrite this rho v term. Rho v is equal to del dot d before. Now I am trying to replace d with electric field strength or electric field intensity E. Here our final aim is we are trying to reduce the variables or we are trying to convert flux terms into field terms. Here field representation is in terms of E for electric field and in terms of H for magnetic field. So finally we are trying to replace d with epsilon into E. Then this rho v equal to del dot epsilon into E. Here epsilon is permittivity or relative permittivity and this is a constant term. And so we can take constant out of that divergence easily. So then by taking this epsilon to LHS, we will get rho v by epsilon as rho v by epsilon equal to del dot E. And now we can replace here this one rho v by epsilon equals to del dot E. Now to try, I am trying to get a standard form of that equation. For that one, what I am trying to do is I am trying to multiply this equation or this term with conductivity on both sides. Then the LHS will become sigma. Here conductivity is represented with sigma. Sigma into rho v by epsilon equals to del dot sigma into E. And we can write sigma into E as current density J. Then the final term is sigma. Conductivity into rho v by epsilon will become del dot J. And we know the meaning of del dot J from continuity equation. So from continuity equation, what is this del dot J? We can replace del dot J with minus d by dt of rho v simply. So now RHS I am trying to replace with minus d by dt into rho v. So then that before equation will become sigma into rho v by epsilon is equal to minus dou rho v by dou t. Now I am trying to rearrange the terms. This equation is finally changed like this. Now I am trying to rearrange the terms by taking all rho v terms together here or to one side. This dou rho v by rho v equal to minus conductivity by epsilon into dou t. So now by integrating this term on both sides, we will get integral. This will become, by applying integration, this will become integral dou rho v by rho v equals to minus integral sigma by epsilon into dou t. So we all know that 1 by x dx, integral 1 by x dx we can replace with log x. Then it is log of rho v. This term will become log of rho v, which is equals to minus sigma by epsilon into integral dou t equals to t. Plus we are trying to add some constant term. That constant term also in terms of charge, volume charges or initial volume charges, that is log of rho v naught. Then finally here, after applying anti-logarithm to this equation, we will get rho v as rho v naught into e to the power of minus t by tr, where tr is the symbol which is used to represent relaxation time. And this tr is the ratio of epsilon to sigma, which is permittivity to conductivity ratio. And this relaxation time we can call as rearrangement time also. Relaxation time or rearrangement time, both are same. And if you want to take the definition of relaxation time, we can define that one as relaxation time is defined as the time taken by a charged particle in a material to reach 36.8% of its initial value. If you take a charged particle with initial charge as q, now for that charged particle to reduce to 36.8% of its q value, how much is the time taken? We can take that one as relaxation time. And now that is the ratio of permittivity to conductivity. Now here if you observe, relaxation time is inversely varying with sigma, right? This is the relation. TR, relaxation time is inversely varying with conductivity. As relaxation time is inversely varying with conductivity, and if you go for the classification of materials based upon the conductivity property or based upon sigma, for a better conductor, conductivity is greater than 1. So as sigma is greater than 1, or as sigma is large for good conductors, relaxation time is short. And if you take dielectrics case or insulators case, conductivity sigma is usually less value. So as sigma is less, its inverse one, relaxation time is more. And for a good conductor, generally relaxation time is in the order of seconds, but whereas for dielectrics, relaxation time is in the order of days also. And this is all about continuity equation and relaxation time. And next one is Poisson's and Laplace's equations. If you take Poisson's equation, again Poisson's equation is obtained from the Maxwell's first equation. And if you take the mathematical relation of Maxwell's first equation, that will be given as rho v equals to del dot d. And now, similar to before case, now here also we can replace, where d is electric flux density, that can be replaced with electric field strength as d equals to epsilon into E. Then rho v equal to del dot epsilon into E. This data. And finally, as epsilon is constant, we brought this one out of this differentiation, a divergence term. Then rho v equals to epsilon into del dot E. And finally, rho v is epsilon del dot. And if you recollect the relation between electric field strength and the potential, electric field strength is equals to minus del v, which is electric field strength equal to gradient of the potential. Then E can be replaced with minus del v. So finally rho v equals to epsilon del dot, and now here we simply substitute the value of electric field strength in terms of potential. Then it is minus del v, del into del. So divergence of a gradient will become this one, del square. So then this equation rho v by epsilon equals to minus del square v. This Poisson's equation gives the relation between potential term v and the volume charge density rho v. So final equation, our final relation which gives a relation between rho v and v, our volume charge density and potential is del square v equals to minus rho v by epsilon. This equation we can call as Poisson's equation or Poisson's law. With the help of this Poisson's equation, we can calculate the potential v. And we can calculate rho v also. And next we have one more special case for Poisson's equation. In that special case, we can call Poisson's equation as Laplace equation. And the special case to get Laplace equation is the region must be charge-free region. If we have a free charge region or charge-free region, then volume charge density equal to 0. In that case, as rho v equals to 0, now that is the condition for free charge region or charge-free region. Charge-free region, both are same. For that case, rho v equals to 0. As rho v is 0, del square v equal to 0 because LHS side is 0, right? So the equation obtained for Laplace equation is del square v equals to 0. This equation we can call as Laplace equation. So generally Laplace representation in Cartesian coordinate system is del square v, where v is potential, which is a scalar parameter. So that one we can give as dou square v by dou x square. That means here variation of potential with reference to 3 coordinate variables. Here in Cartesian coordinate system, 3 coordinate variables are x, y, z. Then del square v here represents second order differentiation of scalar potential with reference to 3 coordinate variables. Those are dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square. Here the variation of potential with reference to all 3 coordinate variables, sum equal to 0. This is about Laplace's equation. If you go through the applications of Laplace and Poisson's equations, those are helpful to measure potential at any point in between 2 surfaces when potential at one surface is known. As the equation relates potential and charge density, we can calculate potential easily. Potential in between 2 surfaces also we can calculate, as we know the potential at one surface. And we can also obtain the capacitance between 2 surfaces. This is about Poisson's and Laplace's equations. What we can conclude for this Poisson's and Laplace's equations is Poisson's and Laplace's equations will relate charge density in case of a volume with the potential. That means we can relate rho v and potential v. And we can use these equations to calculate both potential and capacitance values. Okay. This is all about continuity equation, relaxation time, Laplace and Poisson's equations. Okay. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.